Okay, welcome everyone. Thanks for connecting from all over the world. It's my pleasure to welcome you and welcome our speaker, Radu Krayu from the Department of Statistical Science, University of Toronto. We will talk about Bayesian computation strategy for big data and intractable models. Thank you.
Thank you, Masi, and hello everyone. It's I can say good morning, good afternoon, and good evening, I think, to everybody around the world. Yeah, so today I'll talk about some work that has been recently published. Maybe it's not so recent, but I will refer to also other things that we did more recently on this project with my former student Evgeny Levy. Yeah, so let's start by posing a little bit the lay of the land, talking about what do I mean by MCMC at the crossroads. So essentially what I argue, and I don't think I'm alone, is that large data and intractable likelihoods, or more and more complex models that involve complicated solving maybe differential equations and so on, have brought traditional methods for Bayesian computation at a crossroads. And we see a lot of developments in recent years along the lines of solving or addressing these issues using various approximations, including things that deviate from classical MCMC, such as variational Bayes and so on. Now, I will stick with MCMC in this talk, and I will talk about approximate versions of what you could call exact MCMC. So to, again, make sure that everybody's on the same page in terms of notation, we are having observed data, why not, likelihood function or sampling distribution if you prefer, prior P of theta, and theta is d-dimensional. And the focus is on the posterior. And I will probably use a lot the Metropolis Hastings sampler in this talk. So it's one of the algorithms that perhaps is most responsible for how popular this method is. And the steps are there. You probably know them. To this audience, I don't think I need to go through them. But in red, you see what the quantity that is under question, right? So this posterior, which is proportional to the sampling distribution and the prior distribution, the product between these two, needs to be computed. And clearly, if the likelihood is not tractable, that's a problem. But also, if this calculation is very expensive, it's also a problem, right? So the first challenge I would say is that traditional Bayesian computation faces is that the likelihood is computable, but data is massive. And over the years, we've seen, starting with around 2012, I think, a number of solutions. These are, by the way, I apologize in advance. I probably omit some references, important references. These are some of the things that I read recently, and if you go to these papers, you'll find the original ideas mentioned in the references. So precomputing is an interesting idea, and I think it's practical for people who have multiple processors. They could do parallel processing in advance of starting the simulation, sequential processing, where maybe not all the data is needed to decide and accept or reject. Things of that nature. Divide and conquer is something that is very popular, and subsampling recently has taken off as another possible alternative. Now, I'm going to talk. I cannot talk about all of these, and I don't want to talk about all of these because these are, with very small exceptions, not my work. So I just want to say a couple of things. The divide and conquer is something that we in our review paper is going to appear next year in annual reviews. We looked at various methods, and divide and conquer works very well as long as the posterior is not too far from a Gaussian. And there are many versions of this. Increasingly, increasing in sophistication and complexity. And you can look at those references I listed before. But the idea is to divide the data into batches and to distribute the calculation, the Bayesian calculation, into these K sub-processes that are targeting to K sub-posteriors. And these K sub-posteriors, depending on who you read, have different forms, right? So they could be, they either raise the likelihood to a power and the prior or leave the prior alone, or the other way around, or even raise both by some powers. And depending on the values of A and B, people think about recombination strategies for these samples obtained in each sub-posterior. So they recover the characteristics of the full posterior distribution as much as they can, right? There's always a little bit of a loss, unless we're in exactly Gaussian case. But of course, this major challenge here is to move beyond that. And also, how do you do this if your data is not, it's not independent, right? So if you have an enormous time series, how would you do it? Among the subsampling strategies, recently I've looked more carefully at this work by Quiroz and his co-authors. Some of them are online. So the main ingredients of essentially many of the methods that address the challenges I mentioned here are pseudo-marginal. The pseudo-marginal method due to Christophe Andrieux, Gareth Roberts, Matti Vihola, Arnaud Doucet, and others, obviously. And for this particular method, also the control variates plays an important role, which is something that I always pay attention to. So to give you an idea, the overall idea is to, at each step, to use only a subset of the data and not all the data. Therefore, reduce the amount of computation needed at each iteration of the metropolis hasting. So you can think of a very simple method. Any subsample will give you an unbiased estimator for the log likelihood, right? But clearly, as we know from the work on pseudo-marginal MCMC, the variance of these unbiased estimator is very important. It's crucial to the performance of the method. So the authors are clearly aware of that, and they introduce control variates that are defined as here, where in this case, the control variates are developed in terms of, from an expansion of the log likelihood, the ice term of the log likelihood, around some central value, to say the MLE. And I suggest you look at the paper. It's very interesting. I think it opens many directions for future expansion. Second challenge I mentioned before, when the likelihood is not computable, but one can sample for any value of the parameter, you can sample pseudo data from the sampling distribution. Two large groups of methods have emerged in recent years, and one is ABC and one is BSL more recently. And Dennis has been central to the development of ABCs, and others probably online. I have not looked at the whole list, and it's great you're here. And BSL, of course, Leah Thaus-Price, Chris Giovandi, and their co-authors have pioneered this method. Okay. But the motivation, the real motivation for our work with Evgeny was, what do you do if you have some sort of double threat here, right? You have both large data and intractable likelihood. And by large data here, I mean expensive data to generate, right? So for instance, in climate change scenarios or hurricane surges, generating the data like the one you observe involves complex processes that could be very costly in time, right? So actually running the ABC and ABSL could be expensive. So I also want to challenge a little bit the audience here and say that most of the methods that address the challenge of large data cannot be used directly for intractable models. For instance, both methods that I discussed today are tricky to use with intractable likelihood, simply because, first of all, in the divide and conquer, you have trouble figuring out how far you are from Gaussianity. And in the subsampling methods, you will have to, you don't have access to all these nice tricks that allow you to reduce the variance, right? So this is something that I think this confluence of problems, double jeopardy, I call it, it's actually something that kind of is maybe less addressed than it should be. Moving forward, I can see that data will be bigger and bigger, and this will become more relevant. Okay. So today, that's the plan for today, to discuss something that could be used with these, which obviously this is just a big first step in this direction. There could be many other things that could be done. So IBC is a remarkable algorithm. We all agree that. That's why we have one world ABC. I don't feel like I have to spend a lot of time on this slide, except to say that in marjoram algorithm, the target is this pi epsilon theta y given y observed. But if we take the marginal in theta, obviously you'll have this form, right? So the pi epsilon in theta given y naught is going to be proportional to the probability that the distance is less than equal than epsilon given theta, a theta, and the observed data. So this is what we're going to target. And again, not needed here, but we don't want to sample from the prior, because especially if you have a prior data conflict. And so we are going to consider a chain with this marginal target in theta, and I'm going to call h of theta is this probability. So if I simply use a metropolis Hastings with the target pi epsilon, I will need to be able to compute these things. So of all these things, h of theta is clearly the troublesome one. And looking at the literature, I'm sure there are more recent references that I missed, but you could generate independently pseudo data to estimate this h. You could use smoothing kernels, as in Wilkinson, or you can even use one. All of these are unbiased estimators, but clearly the variance will be a problem. So, and also generation, right? Because the main, as I said, the main issue here was the generation of this pseudo data will be expensive if, let's say, J is fairly large. If J is 1, you don't have the cost, but you have the variability that kicks in the pseudo marginal theory. So the idea, it's actually quite simple in its form, and it's about a statistical. It's in fact, how can we estimate this probability using past proposals? And let's assume that at time n, the proposal is in theta, I call it psi, and the pseudo data corresponding to that proposal is W. Okay, so only a single pseudo data. Let's not forget that at this point, all the proposals in the past, accepted or rejected, are available, along with the corresponding distances which have been computed, right? So we will call this the history, and I'll call it Z, calligraphic Zn minus 1. I'm going to just call it Zn minus 1 is the history of the chain. Okay. So now, given a new proposal of my MCMC ABC metropolis Hastings sampler, I create a zeta star, I have W star, and I will compute the distance corresponding to pseudo data. And now I can create a bigger history, and I can essentially, I want to compute the H that I need, H of estimated, rather, H of zeta star, using essentially a kernel, a nearest neighbor estimator. And so weighted means, these are, you know, we can choose various, we played with various values and so on. And alternatively, if you don't want to use the whole history, which grows maybe, you can use a subset of size k. So some of you may be wondering how this works and how this is comparing with, let's say, how does this fit into the pseudo marginal? And the reality is that it doesn't, right? Because we are replacing an unbiased estimator with a consistent one. So, but there are some things that I think are kind of intuitive here. So let's suppose your distance, the proposal you have produced, has a distance that is greater than epsilon. So if you are using on a single calculation, a single pseudo marginal, you'll either you'll reject, right? But when you take into account the history, it's likely that now your probability of acceptance will no longer be 0. Okay, so that's one observation, that having these history, even things that were bad once, because that's a thing that we actually understood when you run an ABC. If you generate a proposal and you reject it, it's not necessarily that proposal is bad. In fact, that's true in any MCMC algorithm. It's if you try it again later, you may accept it. And therefore, these past attempts, we recycle them. We don't throw them away, even if they were rejected in the past, right? Because in some sense, you put so much effort to generate them, you have to make sure. And if they're always away from from any theta that is likely to be accepted, they will not play a role. But you'll see in simulations that this actually indeed increases the acceptance rate quite a bit. So what we see here, it's a little bit of an interplay. So when k is small, if the original k is small, we will reduce variability, because with a small k, the unbiased estimator is very variable. This will increase likely the number of candidates which are close enough to the proposal, right? So because maybe I should have commented a little bit more, which elements in the history will play a role in this estimator are the ones that are close to the proposal in the theta scale, right? So in the theta scale, if they are close, they will play a role, so their distances will enter into the estimation of H. Okay. So having a larger history will essentially become an effective K that is much larger than maybe a small k. So then, however, if you want to use a large K and the unbiased estimator is great then, but of course it comes with a cost, right? So if K is large, we will likely reduce the cost, because in this approach, we produce only one pseudo data, while in the other one we have to produce K. Anyway, so that's kind of the basic idea. So now I presented this algorithm in that form because it's actually simpler to present the idea, but there are some complications. So if, for instance, the past samples are used to modify the kernel, which would happen if indeed all the proposals accepted or rejected are in the history, then we're talking here about an adaptive MCMC. And clearly with ABC, adaptive MCMC conditions are tricky to verify, especially containment. Now, we have other ways to bypass containment, for instance, adapting on a compact and leaving it the way it is outside a compact. But we said, okay, let's avoid the adaptive MCMC complications, which I think is a great future project for those who are interested. but we're going to generate two. At each time, we generate two pairs, Xi and W, and one we use to update the chain, and one we use to add to the history. So that's how we bypass this past dependence, dependence on past draws. Okay, so in this way, the history and the trajectory of the chain are independent. That's the idea. And so we use the k-nearest neighbor because it has a property of uniform consistency, which is useful in our case for the theoretical results. And to our surprise, the weights, we spent a lot of time on these weights. We thought it'd be very clever and use some of Michael Gutman's ideas, perhaps, or to regress theta on X, on pseudo data and all that. And it actually matters less. So in fact, can use even uniform, so the weights can be one in a certain, hard thresholding, or we have this sort of very linear decrease in the weights, which should work fine as well. So that was a nice surprise, I guess, although a little bit disappointing from a research point of view, because we like complicated stuff. Now, moving on to BSL. I think I always start the BSL presentation with this indirect inference story. So there are better references about indirect inferences, but this is how I learned about indirect inference. So I'm being honest when I put this reference, but now I know that it goes back to Gurria-Roux and others, but in economics literature. So we have a complex model. Is the ABC setting, right? And the idea here is to have a simpler model that approximates well the complicated model, but with a parameter. The simpler model, which is tractable, has a parameter of higher dimension. And then through this model G, we actually reach inference for model F, either in a frequentist sense or in a Bayesian sense. And the idea is, okay, we need to estimate the link between phi and theta, right? And we do that via simulation. And again, this is a very neat and general idea with many complications, in fact, sometimes. But BSL, Bayesian synthetic likelihood, proposes the simpler model that is a Gaussian, right? So the Gaussian model will be the approximating model to whatever complex model we have, and yeah, the details are there, right? So we work on the scale of a statistic, just like ABC. By the way, I don't touch that. That's choice of the statistic is a big question, and there's excellent work that addresses that by Fernhead and Dennis and others. Sorry, let me get some water. So we assume that the conditional distribution for user-defined statistic S given theta is Gaussian with parameters phi, which in this case are mu and the parameters of a Gaussian, right? And the synthetic likelihood associated with theta will be the density of a normal with these parameters, mu and sigma, calculated at the observed value of the statistic. And from once you have a synthetic likelihood, you can also define a BSL posterior. Okay, so the acceptance ratios. So let's forget about the last sentence on the slide. Let's start from here. So how would we sample from that posterior? We would use again an MCMC, a Metropolis Hastings, and in order to do that, we need to compute the synthetic likelihood. And in order to compute the synthetic likelihood for each value of new theta, we will need to compute mu and sigma, and these will be based on generations of pseudo data, right? You generate pseudo data, m of them, you compute the statistic, and then you estimate mu and sigma trivially, but this again implies a lot of generation. So in this case, we can see easily how the previous ideas apply here as well, because now instead of having these unbiased estimates for mu and sigma, we could have consistent estimates based on k nearest neighbor approach. So I'm going to present the same idea, but from a different point of view. And this is the point of view of precomputation. Some of you probably already figured out that in the previous setup, at some point I mentioned on the slide, but I didn't say it, that we will sample from an independent metropolis, also to separate, again, the trajectory of the chain from the history, because if it's a random walk, that separation no longer exists, even if I generate 2 copies. So clearly, I could do that ahead of time, given that it's an independent metropolis. So in fact, this is the approach I propose. It's the same approach, but from a different point of view, right? So we have a proposal Q. We can pre-compute the history, and let's say that for a 1 value of theta in the pre-computation, we compute m statistics. So in other words, we do the pseudo data generation m times and create this vector. Clearly, you want m to be as small as possible, and in fact, we use m equal 1. So you just generate, and this can be the secret of precomputation. Why it's important is that you can divide it among many processors. Right? This is nowadays considered not that expensive, and people can do it. So if you have an important problem that you want to solve quicker, you could do this. And then we follow the approach that I mentioned before. Okay, so let me close with, I think Masi, you told me between 30 and 45 minutes, something like that?
Yeah, 45 minutes is fine. It's totally fine. So
okay, all right. So I don't have to go super fast. Okay. Here the theory I present in this here is we assume that I is a compact set. So this, from this point of view, we could think about adaptive MCMC as well, with some problems with diminishing adaptation, but that's if you want, maybe for the discussion. We assume Q is a continuous density. That's a proposal. That's not a problem. The prior is a continuous density. H of theta is continuous function of theta. So that in the paper, we have other conditions that kind of lead to this. So remember, H of theta is the probability the distance is less than epsilon between in the S scale and the scale of the statistic. So if you think small variation in your parameter will make your statistic jump big values, then this may be something that is not realistic. But it's hard to think of examples like that from what I've seen. And we have some assumptions about the estimation on the k nearest neighbors. Again, that's for convenience. That's probably the smallest k we can take. So then we will call P the transition kernel of the exact MCMC ABC sampler, right? So if I'm able to compute H of theta exactly, P would be the resulting transition kernel. So this is so what exactly are we trying to prove? We're trying to prove that these methods that we discussed, who create a perturbation of the transition kernel, will not push the stationary distribution, the target of these perturbed Markov chain, too far from the target that we started with, right? So we are not trying to do better than ABC. We're in terms of the target, right? We're just trying to say that by modifying, by removing, let's say, an unbiased estimator with a consistent one, we're not going to go out in the woods and lose track of what we're trying to estimate. All right, so we're going to call the stationary distribution of this kernel P is mu. In the ABC, that was pi epsilon. In the BSL approach, it was the Bayesian, the posterior corresponding to the synthetic likelihood, and so on. And we call the approximate kernel at time t, PT. So by approximate kernel, we mean the perturbed kernel, right? And the distribution of tau t is obviously of this form, where nu is the initial distribution at time 0, starting initialization of the chain. All right, so so we have a total variation theorem, which shows that the distance between the distribution at time t and the stationary distribution of the unperturbed chain is bounded in things that depend on our choice, the m and the epsilon. And similarly, you have for an f that is bounded, you'll have a vanishing mean squared error, which again, the bounds is controlled by the norm of f and things that are within our control. So there's other results in the paper here I presented just briefly, and they are both for ABC and BSL. Okay. So this looks very difficult to read, and maybe it's not easy to read everything. We looked at various measures of efficiency, and we have to account in our paper. We have examples where there is no MCMC, pure MCMC sampler. There's always either an MCMC ABC or an MCMC BSL sampler for the target, because the target is intractable, right? So we compare in terms of performance of the approximate chain and the exact chain. And by exact, I mean ABC or BSL, right? Without any perturbation. But we also have situations in which we know we have a well-performing MCMC chain, and then in that case, or even have simulations with true values. So in that case, you can look at things like bias, variance, and mean squared error. And clearly for us, important is here effective sample size as well. It's very important, the computation time. So the CPU time is integrated into all this by looking at something like the effective sample size of a CPU time. Okay. Okay. So an example is, a simple example is the recurse model, which is there. We define the summary statistic using this 14-dimensional vector. And so to compare, this is ABC with a random walk metropolis. Nothing is perturbed. The red line are the true values. And then you see the autocorrelation function for this is quite high. Sorry, I don't know if you can see, but theta 1 has ACF going up to 600, 700 perhaps. Same for theta 2, and for theta 3, it seems to vanish around 250. Okay. This is for ABSL. So it's a MCMC BSL with the perturbation. Okay, so we see a smaller for the first two components. They seem to be, the ACF is looking much better, but the surprise is the approximate, the perturbed ABC, right? So the perturbed ABC, you can see that it's mixing a lot better, and the autocorrelation function is tapering off a lot sooner. So we're looking at 10 here, maybe 20, and so on. So for this example, where this chain is more stable overall, and we think the best ABC in terms of MCMC and ABC is the sequential Monte Carlo, and that's we can ignore the effective sample size in this because it's not relevant. These calculations are not correct for SMC. But if you compare with, in terms of mean squared error, the ABSL in this case, or even the AABC, is not far from it, right? In fact, it's actually better. But this could be, noise. But anyway, I don't want to claim that we're doing better, but they're certainly doing much faster. Okay, so the running time is a lot faster. And stochastic volatility. Example, it's a typical example where the target is not, the likelihood is not tractable. Sorry, it's been a while actually, now I'm looking at this. So again, sufficient statistic, and let's look again at the results. I think the sample size in this case was 500. So let's assume this is 500 here. That's not right. That cannot be right. Maybe 1,000. Anyway, I have to go back and look at that. Sorry about that. But comparison with ABC standard random walk is astounding, and the mean squared error it's smaller, and so anyway, the results are promising, but I cannot, like with these simulations, it's always you can find examples where things work and examples, but in the examples we tried, and we looked at other ABC papers and so on, so that's how we ended up with these examples. The reduction in computation times are significant, orders of magnitude, and the loss in mean squared error is not worrisome. In fact, a lot of times we improve. So the reason I presented the approach for the ABC the way I did is that when it is clearly in our mind, it was this adaptive idea, right? It was this idea that as you progress, you add to the history and use that history for future updates. Now we moved away from that because of the adaptation, but Evgeny ran some simulations where instead of an independent proposal, we actually run a random walk metropolis. And the results are better, right? So they're as good or better than independent. Not surprising. And unfortunately, the theory is not fully developed. And the theory is not fully developed because when you use this k-nearest neighbor updates, estimates, diminishing adaptation can be tricky because you never know exactly how many elements will be near enough, right? So sometimes you may have many, sometimes you may have only a smaller number. We do not put a boundary on how many we have. So that's, I think that requires, in order for diminishing adaptation, you have to somehow show that the number of elements in each estimator increases as simulation progresses. So you want that ratio to stabilize. So as you move on and on, you're not changing it too much. So that's a bit tricky, and that's why you're not seeing this talk with a random walk metropolis instead of independent proposal. And I want to say that these approximate methods have many problems, and people here are familiar with them and are working on them, and they're making progress. But the computational burden is also something we should keep an eye on, because, as I said, models will become more complex. Also, they're becoming more complex because we have more data. So divorcing these two challenges, one from the other, is probably not realistic. So that's, I guess, maybe the best message I can send at this talk. And all the papers are available on my website, and I'll share the slides. And thank you for your attention.